Okay, and for our final talk of this section, we have to talk on cuTile, so go ahead and take it away.
Thank you very much. I'm very glad to be here. My name is Bryce Adelstein Lelbach. I am a principal architect at NVIDIA, where I lead programming language design and evolution. So my job is to make every major language a GPU language, from Fortran to C++ to Python to Rust to maybe someday JavaScript. I'm involved in the leadership of many programming languages. I chaired the Standard C++ Library Evolution Group and the American Programming Languages Standards Committee. And today I'm excited to share with you a preview of a new programming model and compiler stack for CUDA that we've recently announced called cuTile. But first, what exactly are GPUs and what are they good for? So modern CPUs and GPUs are both general-purpose processors that can run almost any kind of code. They differ in what types of workloads they are optimized for. CPUs are optimized for latency. They have more powerful cores and threads, but less of them. They have less latency to access memory and more memory available to access at the cost of lower throughput. Now, GPUs are optimized for bandwidth and parallelism. They can run hundreds of thousands of threads. Their memory latency is higher, but memory throughput is much greater. Now, today, there's two main ways to program GPUs. The first is grid-level models, where you invoke GPU algorithms on the entire input, like an entire array. And the algorithms are launched from the CPU, but run on the GPU. So you don't explicitly parallelize or partition the work or data. The system does this for you automatically, deciding how to divide up the problem and map it to execution resources on one or more GPUs. This is the easiest and most common approach to GPU programming, and probably the one that most people are familiar with. There are many excellent GPU-accelerated libraries that embody this grid-level programming model, such as CuPy, PyTorch, cuDF, cuBLAS, cuFT, and Thrust and cub. Libraries should be the first thing you reach for when writing GPU code. It will make your life easier, and it will often give you better performance because they're written and tuned by teams of experts. You should try libraries before you write your own GPU algorithms. For almost every use case that you can imagine, there's an existing GPU-accelerated library. And if there is, then you should try it out and benchmark it. And if it delivers the performance that you need, then just use it. Don't reinvent the wheel. But sometimes there's no library that does what you need, or you've tested and found that you can't get the perf that you need with the libraries that do exist. And that is when you should consider writing your own GPU kernels. So a GPU kernel is a function that is executed in parallel by a group of threads. All of those accelerated libraries are implemented with GPU kernels. Historically, GPU kernel authoring has been pretty low-level task that's been done in languages like C++. In more recent years, you've been able to write GPU kernels in Python with things like NumbaCUDA, but it's still been a fairly low-level task. Today, when you write a GPU kernel, you're programming at the thread level. You explicitly write code that every thread will run on the GPU. So you decide how to split the compute work into blocks, how to divide the data into tiles, and how those blocks and tiles get mapped to threads. Writing CUDA kernels gives you complete control, allowing you to program and tune every aspect of the GPU. In each new generation of NVIDIA GPUs, we expose more tools, giving you greater control and freedom. But all of those choices can be a bit overwhelming. It would be nice if we had a higher level abstraction that succinctly expresses kernels and allows the system to select which tools to implement them with. NVIDIA GPUs have had tensor cores to accelerate operations like matrix multiplication and convolutions since the Volta architecture about 8 years ago. And in every GPU generation since they were released, the structure of the tensor cores has changed. The formats have changed, the precisions, the width, the mapping of tensor cores to threads are all different across architectures. And this has forced users to rewrite tensor core code for every new GPU that we release. And so what we need is a middle ground, a model where users explicitly partition work and data, exposing parallelism, but that partitioning is logical, not physical. The system decides which tools to use. It will map the partitioned work and data to threads and execution resources for you. Because the mapping is implicit, it is portable. The system can pick different mappings for different NVIDIA GPU architectures. In this approach, we get much of the control and flexibility of thread-level programming, but we also have high productivity and portability like grid-level programming. And we call this approach tile-level programming. And this model is coming to CUDA soon. We've recently announced cuTile, which is a tile-based kernel programming model for NVIDIA GPUs. It is higher level and array-based, and it automates block-level parallelism and memory movement. We've built it to simplify GPU programming and to improve portability for new hardware features like tensor cores. And cuTile is built on top of TileIR, which is a novel, low-level compiler stack and intermediate representation for tile programs that we've developed. cuTile Python kernels are JIT compiled to TileIR using an execution model that allows the code to be executed without the need for a Python interpreter, similar to Numba's no Python compilation mode. And all of this will be released soon. cuTile is simpler and higher productivity than SIMT programming. You should be able to get good performance faster with it. With cuTile, you don't have to decide how data is loaded, mapped to threads, and stored locally. The system does that for you. You just express your computation as array operations. To reach speed of light for a mapmul before cuTile, you'd have to write something like the CUDA C++ code on the left, which is no easy feat. It's also not going to be portable. The code that you'd write would change from GPU architecture to GPU architecture. With cuTile, we can write the simple code on the right and get good and portable performance. cuTile will be exposed first in Python, but a C++ dialect is also coming, which will be intentionally similar to what you've seen, but uses modern C++ idioms and best practices. So now let's explore how the tile programming model differs from the traditional CUDA programming model, which is called SIMT. In CUDA SIMT, the unit of execution is a thread. You write functions that are executed by many threads at once, and we call these functions kernels. The set of threads that a SIMT kernel runs on is called a thread grid, and it's hierarchical, organized into different subgroups of threads, warps of threads, then blocks of warps, then clusters of blocks, etc. Users define the shape of this hierarchy and explicitly program to it. In cuTile, the unit of execution is a block. A block is a group of threads or execution resources that has a single thread of control. You write tile kernels that are executed by many blocks at once, but each block only executes the kernel once on that control thread. In SIMT, the unit of data is individual elements. You write scalar operations on elements that each thread performs. If you want each thread to apply an operation to multiple elements, then you'd write a for loop. There are no native array operations in CUDA SIMT. On the other hand, in cuTile, everything is an array. You express block-wide operations on entire arrays. In both SIMT and tile programming, the user is responsible for splitting the computational work into blocks and dividing the data into tiles. The key difference between SIMT and tile is who is responsible for mapping blocks and tiles onto execution resources and memory. Once you've partitioned your work and data, exposing parallelism, there are still decisions to be made. What elements of data will each thread work with? Where does each thread keep copies of those elements? How should those local copies be laid out in memory? How does each thread load and store those elements from global memory? How does each thread perform computations? In SIMT, the user is responsible for answering all of these questions by picking from the many tools that are available. But in Tile, the system makes those decisions, analyzing the program and selecting the best tools for whatever target NVIDIA GPU architecture you're currently running on. All that we have to do is explicitly parallelize by dividing the problem up into blocks and tiles. And within each block, everything is single-threaded, and you just perform array operations on tiles. So let's look at an example. When running a SIMT kernel, each thread within a block will execute the kernel. But a tile kernel is run by just a single thread per block. Within a tile kernel, we create tiles, which are a special type of local array that you can perform array operations on. Those array operations are sequential with respect to the control thread, but they may be parallelized under the hood by the system using the block's threads and other execution resources. So if you know how to use NumPy, then you know how to use cuTile Python. Here's an example of softmax written in the left in straight NumPy and in the right in cuTile. cuTile is fundamentally array-based. It's inspired by languages like APL. There are two kinds of arrays in cuTile. Global arrays are typical NumPy-like mutable arrays that are accessible by all tile blocks. They are mutable. If you modify their contents, any other references to the underlying data will see the changes. And they are passed in as kernel parameters or globals. You can only perform a limited set of operations on global arrays in tile code, most importantly, loading from them to create tile arrays or storing tile arrays to them. Tile arrays are immutable NumPy-like arrays that are local to a block. Operations on tiles always return a copy, not a view, and those operations are parallelized across the block. Most of the operations that you can perform on NumPy arrays will be supported on tiles. These array operations are going to be parallelized using the block's execution resources. But from the perspective of the block's single thread of control, these operations are performed sequentially. All of CUDA's underlying launch APIs support both SIMT and tile kernels. Users don't have to care how a kernel was written, be it SIMT or tile, to use it. That means you can use and integrate tile kernels anywhere that you can use SIMT kernels, in CuPy, in cuDF, in PyTorch, in JAX, etc. Array parameters to kernel launches can be anything that satisfies the DLPAC protocol, so NumPy arrays, CuPy arrays, PyTorch arrays, JAX arrays, etc. Tile arrays have value semantics, which simplifies compiler analysis by eliminating problems such as aliasing. Tile arrays are immutable, and all tile operations return copies, not views. Some NumPy array operations, such as indexing, reshaping, and transposing, typically return views, not copies, when possible. But the tile equivalents will always return copies, not views. You can never modify the contents of a tile. So assignment to the elements of a tile is ill-formed. You just can't do that. If you need to change the value of some of the elements, then you'll need to make a new tile. And you can do this with the where operation, which takes a Boolean tile and two source tiles and returns a blended tile that has the elements from the first source when the corresponding Boolean tile element is true, and the element from the second source otherwise. Now, it's a little unnerving to think of tile arrays as values because typically our intuition is that it's fine to make copies and temporaries of scalars like ints because they're cheap to copy and they won't always be materialized. But array copies, we typically think, should be avoided because they're expensive and they'll always lead to an allocation and materialization. But tile arrays are different. You should treat tile arrays as you would int. Think of them as being cheap to copy, and they will not be materialized unnecessarily. Imagine a computer architecture where all of the instructions are array operations and all the operands and registers are arrays. That is essentially the tile programming model. So let's look at another example, a tiled matrix multiply in cuTile. We can create tiles with NumPy-like creation operations like zeros. The shape of a tile must be a constant expression, something that is either a constant or that the compiler can see comes from a constant. And there's a few reasons for this constraint. First of all, it creates optimization opportunities. Additionally, tiles may end up being placed in shared memory or some other resource that needs to be statically allocated. Remember, the system decides where the tile will be stored: in register memory, in shared memory, in tensor memory, in global memory, or even in a combination of different memory kinds. The system will also decide what layout the tile will have. This is often tied to what elements each thread will be responsible for when array operations are performed. For example, during loading, we want a specific memory layout such that each thread is loading elements nearby to the elements that their neighbors are loading to ensure that the loads can be coalesced together and issued once for an entire group of threads. This is critical to performance on modern GPUs. Now today, each dimension of a tile must be a power of 2, but this is a constraint that we expect to have only at launch, and then we plan to relax that as soon as possible afterwards. Remember that a block invokes a kernel just once on its control thread, so scalar operations in control flow are executed a single time. And we support fairly arbitrary control flow, so you can have conditionals within a loop, you can have nested loops, etc. Tile load operations create a tile by copying a part of a global array. Load and store operations are indexed in the tile space. So the tile space of a global array is the multidimensional space of tiles into that global array of a certain tile shape. So a tile index ij with shape S refers to the elements of the global array that belong to the ith jth tile. If we provide a different tile shape, the tile indexing will be different, and we will load a tile with a different set of data. Remember that the distinction between blocks, which are subgroups of threads, a unit of execution, and tiles, which are the subset of global arrays, which are subsets of global arrays, a unit of data. A block may work with multiple different tiles with differing shapes originating from differing arrays. The load and store operations are a portable abstraction over the many different strategies for memory movement that are available in CUDA today. For example, load could lower to a traditional synchronous instructions, potentially vectorized, or it could use the asynchronous thread copy instructions available in newer GPUs, allowing the memory movement to be overlapped and pipelined with compute. We could also use the new Tensor Memory Accelerator to perform asynchronous block-wide loads and stores, allowing for even more overlap of compute and I and letting us access the full bandwidth of our GPU. And the system will pick the best option available given the constraints of the memory access pattern, like alignment and stride, etc., that you've specified, and the hardware that you're running on. So next we have a matrix multiplication here. And here we're using a matrix multiply accumulate operation that is unique to cuTile Python. There's not a NumPy equivalent of this. But we would also have the NumPy equivalents matmul and dot and the add operator. MMA, matmul, and dot are another abstraction over hardware. Remember earlier we talked about the differences in formats, precision, width, and mapping to threads for tensor cores across NVIDIA GPU generations. With cuTile, you don't have to worry about all of those changes. You can write tile code once, and the system will take care of mapping it to current and future tensor core hardware. So cuTile is the future of programming NVIDIA tensor cores. Then finally, we have a store, which writes a tile into a subset of a global array. Another way to perform loads and stores is with views. View objects produce new tiles from an input array or tile. A partition view represents the tile space of an array under a particular tile shape. You can index a partition view with a tile index, which loads the tile at that index from the array. You can also assign to a partition view index to perform a store. In a kernel like MapMul, where you are loading multiple tiles of the same shape from an array, this can be more concise and cleaner than calling load. Here's another demo, a non-causal flash attention v2 forward kernel. For a load, we can specify the memory layout of the input global array with the order parameter, which takes the NumPy style argument F for column major or C for row major, which is the default. Now note that this only specifies how the global array is accessed, not the memory layout of the loaded tile. That's up to the system and cannot be controlled by the user. We have operations for combining tiles like cat and subdividing tiles like extract, and operations for reshaping or casting them. Tiles support NumPy style broadcasting. When operating on two arrays or an array and a scalar, the shapes of both are compared element-wise, starting with the rightmost dimension and moving leftwards. Two dimensions are compatible if they are equal or if one of them is 1, in which case the dimension will be stretched to match the other. One of the objects may have fewer dimensions than the other, and if so, then the missing dimensions are assumed to be 1, meaning they will broadcast. At launch, cuTile will support a wide range of numeric D-types, arithmetic, floating point types, and all non-floating point numeric types can be used with all arithmetic and mathematical operations such as addition, subtraction, trigonometric functions, and transcendental functions. Restricted floating point types can only be used with certain operations such as matrix multiplications. You can write and use SIMT and tile kernels in the same source file. We also plan to support hybrid kernels where you can write both SIMT and tile code in the future. So Llama 3.1 is an open source large language model developed by Meta. In the course of just a couple of weeks, we ported Llama 3.1 inference to cuTile and were able to get 93% of cuDNN's performance. And this is with our infant tile IR compiler. Performance will only get better from here. cuTile isn't just for large language models or AI though. This extends the CUDA model and applies to GPU programming in all domains from HPC to data science to computer vision. In just 2 weeks, we ported mini-weather, an HPC mini-app for 2D viscous fluid flow to cuTile. It's a traditional HPC stencil code on a structured grid with a bunch of different physics models, which are shown here. We envision expressing stencil kernels like those used in mini-weather like this. So each block loads one overlapping tile of elements from the global array and then creates a stencil view to that tile. The stencil view can be indexed with relative coordinates, producing tiles of the same size but with the contents shifted. And this allows us to perform operations on neighboring elements. When storing the result, we only want to write the interior points of each tile, so we mask away the other points. Those points will be computed and written by neighbors. So cuTile is a major new addition to CUDA. It's the first time we've extended to a new programming paradigm. But SIMT isn't going anywhere. There are some things that you simply can't express in cuTile, such as implementing synchronization algorithms where threads within a block must explicitly communicate. cuTile is an addition, not a replacement. And we're very excited about the possibilities that cuTile unlocks. Now it will be much easier to write speed-of-light GPU kernels. If you want to learn more about GPU programming, there are many talks available to watch on demand from GTC 2025, NVIDIA's developer conference. Stephen Jones' talk, CUDA New Features and Beyond, also covers cuTile and tile IR. We've also released a new open source CUDA curriculum with tutorials, notebooks, and other learning materials, which you can find on our Accelerated Computing Hub on GitHub. We've also got lots of great courses in NVIDIA's Deep Learning Institute on CUDA and parallel programming. As a thank you for attending today, you can access our course catalog for free for the next 6 months using this QR code, which is also on the next slide. And thank you all for your attention. I've also got a podcast called ADSP. It's pretty good. We talk about algorithms, data structures, parallel programming. Subscribe now, available on all streaming platforms.
And maybe I'm getting this wrong, but I think you were also on Talk Python in the last
I was recently, that's correct.
Yeah, that was a good episode. All right, so thanks very much. That was a great talk. So we have a few questions in chat, and it looks like a few other ones coming in. So maybe I'll start with mine. So if I understood correctly, this is all getting released as part of like CUDA, in CUDA Python itself. So in like the next release of like CUDA, the language with CUDA Python support, this should come in?
I can't comment on specific release timelines. It will be on GitHub at some point. It's not going to be like distributed necessarily only through the CUDA toolkit.
Okay, so it's not that, okay, so it's possible if you already had like an existing CUDA setup that you could install cuTile, an extension to what you already have.
I can't comment more on release plans, I'm sorry.
Okay. All right, so we'll go next to Natty as question. So it seems like this new approach is more suitable for people that are familiar with Python and the PyData ecosystem. So are there or will there be any guides and advice for scientists and researchers on how you would go about porting their existing CUDA kernels and maybe even like legacy ones to this new approach?
An interesting phenomenon we found while developing cuTile is that it is a lot easier to port from sequential NumPy code to cuTile than to port from existing CUDA SIMT code to cuTile, because the sequential NumPy code is expressed in terms of array operations, and the SIMT code is fundamentally expressed in terms of scalar operations. So yes, we will almost certainly provide guidance and tutorials, but the best porting advice that I would give is start from your sequential NumPy code and port that to cuTile. Don't try to take your existing CUDA SIMT code and express that in cuTile.
Okay, great. That's super actionable advice, which is always appreciated. And we've got a question from Nodar. Are there any NVIDIA GPU architectures that cuTile will not be supported on? You already showed that it's going to be supported on at least those three, and you said moving into the future as well. So are there like ones that are too old to be supported?
There are ones that are too old to be supported. I can't comment on the specific ones that will be supported at launch, but I think going forward, this will be supported on all NVIDIA GPU architectures.